In this lecture, you are going to study planar defects or surface defects. Planar or surface defects. These defects are two-dimensional defects. The point defects are zero-dimensional. Then we studied line defects. Line defects are one-dimensional. Then this is the planar or surface defects, which is two-dimensional. These defects separate two regions of the crystals. It separates two regions of the crystals. But after heating the crystal close to its melting point, these defects can disappear. Okay, these defects can disappear after heating crystal to melting temperature. There are four different types of surface defects. The first surface defect is external surface. External surface. Second defect is grain boundaries. Third one is stacking fault. And the fourth defect is twin boundaries. So these are the four different surface defects. Now let's see one by one. The first one is external surface of any crystalline material. Let me show you the diagram. Say this is the block of some crystal material. It has external surface. This surface is external surface. And this external surface itself is defect. Let's see how come this is a defect. Now there are atoms. For that, consider FCC structure. You know that in case of FCC structure, its coordination number is 12. That means every atom is forming 12 bonds. It means coordination number is 12. It means every atom forming 12 bonds with neighboring atoms. Let's say such a crystal is shown over here. It is a FCC crystal. So there are atoms in this crystal. There are atoms which are inside the unit cell. All atoms which are inside the unit cell will form 12 covalent bonds and their energy would be minimum. Okay, in this case, inside atoms, all inside atoms form 12 bonds. Every atom will form with 12 bonds, and its energy is minimum. Energy of each is minimum. All these atoms are at minimum energy. Then let us look at atoms which are on the surface. So here are the atoms. These atoms are on the surface. Okay, here we are considering atoms on surface. These atoms on surface are, there are atoms for this. Their neighboring atoms are only one side and other side is free. So those atoms which are on the surface, these atoms will form four bonds in same plane. They are on the surface. As you know that, the coordination number of FCC is 12. Out of 12, 4 atoms are in the same plane, 4 atoms are in below plane, and 4 atoms are in upper plane. If you consider this atom, then the coordination number is 4 in same plane. That means they will form 4 bonds in the same plane. There are 4 atoms in below plane and 4 are in upper plane. These 4 are in upper plane. That's how there is 12 coordination number. 4 in the same plane, 4 in lower plane, and 4 in upper plane. Now the atoms which are on the surface, these atoms, they can form 4 bonds in the same plane and 4 bonds in lower plane. But there are no atoms on upper plane. So in this case, no atoms in upper plane. So they will not form any bond over there. So out of 12, as you can see here in this example, out of 12, only 8 bonds that particular atom which is on the surface will form with the neighboring atoms. So 4 bonds are free bonds there. And so the atoms will have more energy. So atoms on surface have more energy compared to atoms inside the material. So this is the defect. In terms of energy, this is defect. We are calling it surface defect. Next type of surface defect is grain boundary. We have studied the grain boundary in the polycrystalline metals. In polycrystalline metals, there is a grain boundary. What is the grain boundary? Let's see that. We already studied it, but let me show you the diagram. So there are different grains with random orientation. Suppose this is the one grain which is having the same orientation. Then let's say this one is another grain. There is an angle between them, and there may be some one or two atoms here and there. So boundary between these two crystals or two grain is this. Now as you can see, near the boundary, atoms are not located where they should be. There is an angle. There can be small angle between the boundaries. There can be large angle between the boundaries. There is a tilt between these two grains. And because of that, atoms are not at the position where they should be. So there is a large distance here. In this case, there is a large distance between the atoms compared to atoms inside the grain. And so they have higher energy. Therefore, atoms near the boundary having higher energy compared to atoms inside the grain. You know that this is called crystal or grain. It's called a crystallite or grain. And the boundary between them is grain boundary. So near this boundary, atoms are not at their right position. The distance between them is large, that also depending on whether the angle between them is less, low or high. Accordingly, they are separated. And so they have the higher energy, and so that is the planar defects. Then third defect is stacking fault. Stacking fault. Stacking fault means there is a fault in stacking sequence of atomic layers or planes. We have studied these atomic layers and planes in CCP and SCP structures. You know that in case of CCP, which is nothing but cubic closed packed structure, the sequence of stacking is ABC, ABC, and so on. That is the stacking sequence in case of CCP. In case of HCP, HCP means hexagonal close packed structure. And in this case, sequence of stacking is AB, AB, and so on. Now, in this case, let us consider CCP structure. We are considering CCP structure in which the sequence is ABC, ABC, ABC. Let's say during the growth of this structure, one of the plane is missing. Okay. During growth of crystal, one of plane is missing or added. Is missing or added in it. Added in it. Then what would be the sequence? If one of the plane is missing or if one of the plane is added in that, then you will get the sequence like say A, B, C, A, B, C. Then let's say plane C is missing. Then we will get here AB. Then again we will get ABC, ABC, and so on. So in this case, C plane is missing or C atomic layer is missing, and because of that local sequence becomes AB AB. Because of the C plane is missing, so local sequence become AB AB, which is HCP sequence. So in between there is a SCP region. On either side, on the either side of it, it is CCP, but locally it is SCP. So you can say there is a SCP region, and that is because of stacking fault. Then let's go to twin boundary. Next type, the fourth planar defect is twin boundary. In this case, we are again considering CCP structure. CCP structure. And I am going to show this sequence of this CCP vertically. So this CCP, which is the perfect crystal with no defect in it, you get the sequence A, B, C, A, B, C, A, B, C, A, B, C, A, B, C. How many sequences are there? 1, 2, 3, 4, 5. Let me draw one more. A, B, C. So this is the sequence of perfect CCP crystal. Now Near to this, I will write the sequence CCP with twin boundary. For that, let me consider this A, or let me consider this C plane as a mirror plane. I am assuming that this C plane is mirror plane. And above this mirror plane, the sequence is same. The sequence is A, B, C, A, B, C. So the sequence is same in upper plane. But since this is mirror, the upper structure is reflected in the mirror plane. So what I am going to do, reflect the structure. Let's say that this is my original structure. And I will reflect this original structure in this mirror plane. Reflect structure in mirror plane. So here, instead of A, here is A, instead of A, I will get B at this point. This B is a reflection of this B. And at this point, I will get A. Instead of B, I am getting here A, and this A is reflection of this plane in the mirror plane. Similarly, I will get here C, B, A, C, B, A, C. Then I will get B over here. Then I will get A. So, see how the sequence is changed. In the mirror plane, the sequence is changed to, instead of ABC sequence, I am getting BAC. Sequence is changed to BAC, BAC. This is C over here. Because after A, we'll get C here. So I'm getting C over here. BAC. So the sequence changes from ABC, ABC to changed. Let me write like this. Sequence changed from as you can see here, the sequence is here ABC. In the original, the sequence is ABC, ABC, which changes to BAC, BAC. So this is the block which is actually the mirror image. Block is a mirror image of the crystal above the twin plane. So this plane, this mirror plane is called twin plane. And in this block, or let me write block, block is mirror image of crystal above the twin plane. and we get the new sequence. And obviously, in this case, the orientation changes. In this case, orientation changes. And these two orientations is related by the mirror image. So this is original structure here, and what I get here is mirror structure. So this is the mirror image of the original structure. Generally, the boundary appears in pair. Okay, generally these boundaries, twin boundaries. So this is a twin plane, and the boundary between these two is called the twin boundaries. And these two twin boundaries generally appears in pair. So let's see that. Again, assume that this is our mirror plane. Okay, this one is again mirror plane or a twin plane, or you can say this is second twin boundary. Then we will get reflection. Let us reflect this structure again. So here I will get A. I am getting that A because C is the mirror plane and the structure is reflected in the mirror, and so I am getting this as A. Similarly, here I will get B, then I will get here C, and again A, B, C. See in this block. What happened in this block? In this block, the sequence is restored. So in this case, there are two boundaries, two twin boundaries are there. And the region between these two twin boundary, this region is called twin. The region between them, between these two structures, that region is called the twin. So the first is original structure, second is, this one is the mirror image, and again we get original. Let me show this in two dimension. I will draw the structure here. It takes time. Let's see. So this is the twin boundaries, this and this are twin boundaries, and the region between these two twin boundaries is called the twin. So we can say that twin boundary is a boundary in the crystal on either side are mirror images of each other. Twin boundary is boundary in crystals on either side are mirror images each other, and the sequence is restored if there are two twin boundaries. So that was about the twin boundary. Then let's go to the next defect, which is volume defect. Next defect is volume defect. This volume defect is three-dimensional defect. And volume defects are nothing but big whites. Big whites are produced because there are large number of atoms missing, or you can say it is the absence of large number of atoms. Now, in what way this large number of atoms are missing? So there are two different uh, conditions at which this large number of atoms are missing. First one is air bubble trapped, while solidification of crystal. Okay, during the solidification of the crystal, if there is air bubble, trapped air bubble, then that trapped air bubble will form a big pore. And if there are large number of air bubble trapped in the crystal during the solidification, then what we get is porous material. And this is of course three-dimensional defect, which we are calling volume defect. This is one way. Another is there can be shrinkage of crystal during solidification. If crystal is shrinked, then this produces the cavity. Cavity process is called the cavitation. Large number of cavities will be produced. So this is another way of creating the volume defects. The third way is, what if impurity atoms cluster together? Cluster together. They form small region of completely different phase with respect to parent crystal. So in the material, if suppose if this is the material, and in between there is a material of impurity atoms. it has completely different face. So this is about the volume defect.